welcome to non-IITian. So in this lecture we are going to discuss a problem from ISI JRF 2025 MTA, and the problem is in complex analysis where we discuss about image of an unit circle under certain conditions. If you're enjoying the content, please don't forget to like, share and subscribe to non-IITian. Let us get to the problem statement. So the problem statement is as follows. Let Z1 till Zn be complex numbers such that each of their modulus is 1. Okay, so each of these Z1 till Zn are from the boundary of the from the unit circle. Consider the function f from C to C defined by f of w is equal to w minus Z1 till w minus Zn for all w in C. Prove that the set modulus of fw contains the interval 0, 1. Okay, so that's quite an interesting problem. Let us analyze. Okay, so here are a few things which we would be liking to observe. First of all, observe that the zeros of fw are precisely the values z1 till zn. Okay, moreover, the set C, which is the collection, which is basically the unit circle, it's actually a compact and a path connected set. It's a, okay, so let me just choose the color. Wait a minute. Okay, so it's basically a compact and a path connected set. Fine. But the function which we would be liking to define, h of w is equals to mod of fw. This is a real valued function defined on the complex plane, and since f is a polynomial, it is continuous. The absolute value function is also a continuous function. So h is actually a continuous function from, h is a continuous function from C to R. Now we will also be liking to apply the intermediate value theorem, which says that if h is a continuous real valued function on a path connected set S, then for any 2 points P and Q in S, the function h takes on every value between HP and HQ. Okay, in other words, if I am very strict, this is nothing but saying that only connected sets in R are intervals. So this is actually the compact notion of the intermediate value theorem. Okay, before moving on to the strategy, let us just dive into the problem itself. So the first part, what we need to observe is something which we have already discussed, that the unit circle is a path connected set and h is a function from C to R, which we have defined as h of w is equal to mod of fw. This is a continuous function. Therefore h of C, this should be an interval in R, right? Because continuous image of a connected set is connected and the only connected sets in R are intervals. Okay, is it clear? So that is exactly what is written here. In R, a path connected set is simply an interval. Over R, path connectedness and connectedness are equivalent notions. Therefore the set of values V is an interval. That's exactly what I wanted to say, because V is nothing but the image of H over the values taken from the unit circle, nothing else. So what we do is that we define V to be of this form: a closed interval small m capital M, where m is the minimum possible value of modulus of fw and capital M is the maximum possible value of modulus of fw. Now what is the minimum possible value of modulus of fw? That is quite immediate from the definition itself, because we know that f of w, modulus of f of w, is greater than or equal to 0. So the least possible value of it is obviously 0, and the 0 is attained, right? Because f at any of the zi's is 0. That's exactly what we did here. That let us just choose z1. Since z1 is on the unit circle, that's exactly why it's important here. Modulus of f at z1 is 0. So therefore the minimum possible value of modulus of fw on the unit circle is 0. So our interval of values is of the form 0m, because the minimum possible value we just saw it to be 0. Now if in some way, if we are able to show that 1 is here, then by the intermediate value theorem we will be sure about the fact that this is contained in the required image, right? That is exactly the strategy we skipped, because I wanted to make sure that you will go through it yourself through the proof. Okay, that's exactly what we want to do. So leave this part there. I just sort of experimented with things. Let us come here. See, what is my f of 0? My f of 0 is, if I just put, so my f of z was, sorry, my f of w was w minus z1 till w minus zn. So my f at 0 should be minus 1 to the power n into z1 till zn. This implies that my modulus of f of 0 is nothing but 1. And that's exactly what we need to do, right? Why is it so? Because observe the following. Since f of w is a polynomial, so it's analytic on the entire complex plane. Fine. Now consider the closed disk D. By the maximum modulus principle, we know that the maximum value of the modulus of fw is attained on the boundary of the closed disk D, that is on the unit circle. And we see that the modulus of f of 0 is 1. Therefore, the modulus of f of 0 is less than equals to the modulus of f of w for all w belonging to the unit circle, which we denoted as c here, right? And this is 1. And we know that this should be less than equals to the supremum of all such values, which we devise to be m, right? Therefore, 1 is clearly less than or equals to m. And that's exactly what we proved here. Are you getting my point? So the only thing which we required here was the maximum modulus principle. Hence, we have shown that the maximum value is m, which is greater than or equal to 1. Therefore, 1 is somewhere here, which implies that the entire interval 0, 1, this is contained in 0m, and this was exactly the set we required, right? And hence we have proved or given a solution to the problem which was given to us. Clear? Thank you for watching. Please like, share and subscribe to Non-IITian if you like such solutions. We'll come up with more such solutions soon. Me too, guys.